like be just a short posting. Okay, so some old school definitions. So chemistry. Chemistry, like biology, like physics, it's the study of what? It's all the stuff that makes up the world. Matter. So it is the study of matter and all the changes it undergoes. So we are going to talk about melting, freezing, changing the states of things, boiling water, how those things change the appearance of the matter, but doesn't actually change its substance. But then how is it different when you burn something? So if you burn wood, you can't change it back to the pieces of wood. It becomes ash, and there's no changing it back like you can take ice and let it melt, converting it back into liquid water. So we'll talk about those changes, and then we'll also apply those changes to things like, well, what happens when you eat? What happens to nutrient molecules? So those are irreversibly changed by chemical reactions, and we'll talk about those as we go through the semester. Okay, so that leads to another definition. So matter has two criteria. It's anything that takes up space and has weight or mass. Yeah, do you remember that? You're like, that sounds familiar. Yeah, so matter is anything that takes up space. So that means it has volume and has mass. We always think of mass as being something with weight. Okay? The amount of material that makes it up. So I always tell people matter is a noun. Okay? It's a person, place, or thing. Right? So it is a solid, a liquid, or a gas. So if we were going to do a comparison of things that are solids, liquids, and gases, which of these has particles that are as far apart as possible? Solids, liquids, or gases? Gases. So if I was going to draw gases, like the air in the room, the particles are very spread out. So draw just like 10 dots, lots of space. In fact, the odds of two gas molecules touching themselves, bouncing off each other in this room, almost slim to none. Like they pass in the night. They rarely ever come in contact with each other. Solids, on the other hand, are tightly packed. They are sort of like very organized, rigid in their arrangement. So draw 10 little dots and just put them super close. And then what do you think about liquids?
They're kind of together, but they're spread apart.
A little more apart, right? So liquids, they have a little bit more space between molecules because they flow. So those molecules can flow past each other. They're not stuck in this regular rigid arrangement like solids are. So you can put 10 little dots, just put them pretty close. And then maybe put an arrow to show that they have this ability to move. So they're not like stuck in that position. So they always say then, because solids have this very rigid, regular arrangement, they have a very definite volume, right? So the desk doesn't just change its volume. It has this very definite volume and shape. So some metals, like aluminum foil, you can bend, but they don't just bend on their own, okay? So solids tend to keep their shape, keep their volume. But what about liquids? Which of the two is definite for a liquid? Volume, right? If I have a cup of coffee in a cup, or if I spill it on the floor, it still was a cup. It still was 12 ounces of coffee. Okay, so the volume still stays the same. So this has a definite volume. But what happens to the shape? It can change shape, right? So liquids typically take the shape of their container. Okay, whether you have a tall, skinny glass or a short, wide mug, 12 ounces can have a different shape because they flow. But then what about gases?
they have no volume or shape.
Yep, no definite volume or shape. It's, in fact, if you have, see, in a tank of oxygen, so a patient needs oxygen, so you buy oxygen in a tank, it's compressed oxygen. So instead of it being part of 21% of the air is oxygen, so they concentrate the oxygen and they put it into this tank so it forces those gas molecules together. And then when you begin to release the pressure, you open the valve, what happens? The oxygen flows out, right? Flows out through a tube that you can then use for a mask to try to increase the oxygen content in the air your patient's breathing. Whether you're talking about four-legged or two-legged, you're still going to use it that way. So they have a variable shape and volume. Gases like to spread out and take whatever the shape of their container is, and they can expand to fill a variable volume, and we can compress them. You can think of an O2 tank as being a good example of where oxygen, instead of being far, far apart, those molecules are pushed into a small space so that the tank is small, so that it's easy to transport it from one place to another. So all of these are considered matter. We can have changes in this matter. We can take water, freeze it, and make ice. We can take water, boil it, and make steam. So matter can be converted from one visible appearance to another. But what's not matter? So energy, okay? Because there's these kinetic and potential types. Energy is not matter. I always say energy is a verb. So energy is the ability to do work. Yeah. So see, those things just kind of come out of your head every once in a while, like just that memory of them. Hopefully it's not a bad memory. Hopefully it's like replaced with good memories now. Okay, positive memories, enjoyable memories. Energy is the ability to do work. So you can usually see the effects of energy. Okay, so where in this room is there energy that's being used?
Our hands, right?
Mechanical. Right, so mechanical is the movement. So writing with your pen, walking to class, swallowing your water, all mechanical, any kind of movement. What else in this room?
Our brains.
Okay, so chemical energy. So maybe you ate breakfast, which you're now digesting. So that means that your stomach acid is breaking bonds, breaking proteins, carbohydrates, and fats into smaller and smaller molecules. Those are going to get absorbed so that your cells can use them for energy, brain cells specifically. So this is the energy that is contained in chemical bonds. What else? Mechanical energy, chemical energy. If you put your hand on the table, how does it feel? It's what? Okay. Well, compared to your face, it is cooler, right? That's thermal energy. So thermal energy is heat transfer. Things going from warmer to cooler. Okay. So that transfer of heat. If you walked outside, it's just like, gosh. It feels like it hit you in the face right now. I mean, like 8 o'clock this morning, I was like, wow, like a lot of heat and humidity. This is probably like the hottest day we've had yet this summer, just really muggy and steamy. A lot of thermal energy going on out there. Okay, what else in this room? Mechanical, chemical, thermal. Lights or what?
Electrical?
Electrical energy. So electrical energy is the flow of energy through a wire. All examples in here. We will talk about nuclear energy, which is like radioactive elements. This is the energy that you find in an atom. So all of these examples, they can be kinetic or potential. Kinetic means it's active energy. It's energy that's doing something, right? So these lights in the back that are on, they're kinetic. And all I had to do was flip the switch because that completed the circuit so that electricity could flow through the wire. With electricity, it always has to be able to flow in a circle, okay? And when you shut the switch off, that breaks the circle and that's why the lights go off. So once the switch is flipped, electricity can flow through the wire and that causes the filaments to glow. So kinetic is active, right? I always think of kinetic energy as doing something, okay? Something doing work. So writing, physically writing, that's active. Laying on the couch, that's potential, okay? You're not really moving other than breathing, hopefully, okay? But you're not really doing much in terms of those muscle contractions. So think of muscles contracting, that's kinetic. The lights being on. Whereas potential is inactive. It doesn't mean that it couldn't happen. It just means the condition right now, it's not doing work, but we could change that. So I told you like digesting your breakfast, that's active. That's kinetic energy. So can you give me an example of where that would be potential?
You thought about the cereal?
Thinking is kinetic. But what about the cereal on the shelf? Right? You haven't eaten it yet.
Yeah.
Okay? Okay, so the biscuit's still in the bag. That's potential energy, right? So you haven't eaten it yet. There is chemical energy in those nutrients, but you're not going to get them until you eat them. Okay? So potential is just where the energy's there, but it's not being used right now. So laying on the couch. The lights, not the cough. Just my spelling today. Couch and my pen. And then the lights being off. Good examples. And then an uneaten biscuit. Whereas an eaten biscuit is going to have kinetic chemical energy. So just think of them that way. Think of kinetic as doing something, movement, electricity on, heat being transferred, that's kinetic. But potential is that inactive, could do work, it's just not doing it right now. So we will talk about energy. Chapter 5 really talks about kind of like energy transfer, energy that happens when chemical reactions happen. So we will come back and talk about them as well. But if we're going to split matter, and I'm trying to keep up, 11:45, just keep me on task, okay? When we talked about matter, I said matter is anything that has mass and takes up space, right? So it has to have mass and it has to have volume. But there's a lot of different kinds or ways that you can find matter in nature. So they can be split broadly. Most things are mixtures. But there are some things that exist as what they call a pure substance. So a mixture is when you have more than one type of matter physically combined. Okay? So like your sheets, your soda. Okay? So in your soda, you have carbonated water, there's coloring, there's sugar, there's flavoring. Okay? But those things don't chemically combine, they're just mixed together. Okay? That's a mixture. So this is two or more things. And the big thing is this physically combined. That makes the mixture. Pure substances, on the other hand, if I take a pure substance and I split it into two and split it in and split it and split it, it still is going to be the same substance. Okay? So it's only composed of one thing. This is a single substance, and it cannot be physically divided.
So like water?
Right, pure water, okay? So if we had pure water, that would be a pure substance. So pure substances, I always tell you, here's the easiest way. One, look and see if it's on the periodic table, okay? Because periodic table of the elements. So pure substances, they can get divided into elements which are on the periodic table. And they exist individually, okay? So like if you look, the number 6, C, does anybody know what that is? Carbon, okay? C, H is hydrogen, O, oxygen, and nitrogen. Those 4 elements make up 96% of your body, okay? 96% of the atoms in your body is CHM, carbon, hydrogen, oxygen, nitrogen. It's just how I always remember it. It's not really a word, but it's like one of those weird mnemonics, so CHM. But those, if you find just carbon by itself, that's an element, or just pure nitrogen, or just oxygen in a tank, okay? Then that's a pure substance and it's an element. But then someone asked about water. So what's the formula for water? H2O. So that's one that people typically are comfortable with. But now when I look at this, do you see that that's H2O? Looks like hydrogen and then 2 and then that oxygen. Those are compounds. So a compound is a pure substance, but it is where you have more than one element chemically combined in a fixed ratio. So water always exists as H2O. And what that means is 2 hydrogens, the number after the element always tells you how many of that element. Okay? So H2O means that there's 2 hydrogens and 1 oxygen. And these are chemically combined. So if I take water and I divide it and divide it and divide it, I would eventually get to a small single unit that would have 2 hydrogens and 1 oxygen. So it'll always have that fixed ratio. And I can't physically like boil it, freeze it, filter it. I can't separate the H's and the O's from that single particle. So that's why it's still considered a pure substance, because it's all composed of the same units and I can't physically divide it. So that's always like the first trick is ask yourself, one, is it on the periodic table? Right? So if you see it on the periodic table, then you're like, oh, it's a pure substance, definitely. And then it's an element. But if you're given a formula, so this is what they call a chemical formula. And so a formula actually defines how many of each element is present. So for example, if I have C6H12O6, that is the chemical formula for glucose, which is blood sugar. How many carbons? 6. So if I had a single unit of glucose, 6 carbons, 12 hydrogens, 6 oxygen in that one unit. So that chemical formula defines how many of each atom is present in a single compound, in a single discrete unit. They typically call it a molecule. So a molecule is a way to describe like the smallest possible unit. Sometimes it's an atom, but sometimes it can be just a compound. Okay? But now, what about mixtures? So mixture sometimes requires a little bit of thought. Sometimes you have to know something about a substance to be able to say, yeah, that's a mixture. Sometimes you're like, I don't know, like for example, brass. Okay, so if someone said, what is brass? You're like, I don't know. It's a metal, right? So like if you have like brass candlesticks or brass equipment kind of stuff. But when you look on the periodic table, there isn't an element called brass. And so that's when everybody like gets kind of confused. So that you really need a little more information. So I won't ask you one that we haven't actually talked about. You're not going to see like some random thing and then be like, I don't know what that is. Okay. It'll be ones that we go through, examples that we do. If it is a mixture, then know that it's going to be more than one substance, 2 or more. It could be 2, 3, 4, it could be 50 different substances. They are physically combined. And in theory, you could separate them. Okay. They might be separated, like I said, by boiling. You could separate them by freezing. You could separate filtering, but you could separate them. However, if you look at the mixture and it looks uniform, which means it doesn't separate out, you can't see any layers, can't see any parts or pieces, they call that homogeneous, okay? Or homogeneous, however you want to pronounce it, okay? So homogeneous, the word homo means what? The same, Okay, so the word homo means it's the same. So just think it looks the same. So examples of this, okay? So I like my coffee black. It took me a while to get there though, okay? Like I have adapted. I started off as a cream and sugar person. And so I have slowly like adapted. So black coffee, when you look at it, does it look the same throughout? Yeah, okay? But then what do you know about it? This is where you have to kind of think about, well, what is it made of? Okay? So how did you make it? You had to use what? Water. Boil water and you pour it through coffee grounds. Okay? And so some of the grounds stay behind and then this brown liquid comes through. So that's the first clue. If I start off with two things and now I'm getting this other thing, odds on that that's going to contain, like it contains like the flavors, the aroma molecules of the coffee. It contains caffeine, which is really, let's just be honest, that's why most people drink it. Okay? So it has the caffeine, but then it's got water. So I know that that is a what? It's a mixture. Okay? Things that are physically combined. Does it look the same? Yes. Okay? So black coffee would be a good example of a homogeneous mixture. But now what if you put sugar in it and stir it up? What would you call that? It depends on how much sugar you put in, I guess. Because like my coffee, I could never see the sugar in the bottom. It wasn't quite, my youngest child, yes, she was like a 4 teaspoon of sugar kind of girl. And I was like, just exactly how much sugar do you need in your coffee? I don't really think, she just used the coffee to dilute her sugar, I think, for her morning. Okay, so most of the time you put a teaspoon in, stir it up. Can you see the sugar anymore? No, completely dissolved. So you would say it is homogeneous. Okay, so I've now have coffee with sugar, still homogeneous. What if you throw a splash of cream in? As long as your cream's not bad, there's nothing worse in the morning than that. Like clumpy creamer, ugh, that's the worst. But if I add cream, stir it up, it's still homogeneous, yes? Okay, it still then gets this kind of like milky light brown color. That's still homogeneous. Those are all examples of mixtures. And notice like my daughter used to put 4 teaspoons of sugar in hers. Some people put like just 1. I don't put any. You can vary the composition when you're talking about a mixture. You might like your tea really sweet. She's the same way with that too. Okay? Or you might be like when I first came here and started drinking, I would drink unsweet tea and people would look at me like I was a crazy person. Nobody drinks unsweet tea down here. Then someone said, you know that tea's really old because nobody drinks it. And I was like, what? So I was like, okay, I'll have sweet tea. All right, so coffee with cream. Cream and sugar, same thing. Still homogeneous. So can you think of something that's a mixture that's heterogeneous? Lucky Charms, yes. Okay, so Lucky Charms, because it's got the marshmallows and it's got the crispy little circles. Are they circles? Huh? Okay, the cereal, lots of different colors in them. If you can see colors, you could sort, okay, if you were one of those people. I'm just going to eat the marshmallows and leave behind the crispy cereal. So you could do that. You could sort. You think like M&Ms, you could sort by color, okay? Definitely, anytime you can see any layers, if you can see color differences, if you can sort through things, then you know that's going to be heterogeneous, okay? So I always think of like Italian dressing. Even most ranch dressing has like little things in it. I don't know what it is, but it's pretty good. Okay. So homogeneous, can't see any layers, pieces, parts. Heterogeneous, I can. So we had the Lucky Charms example. Italian dressing. Okay. Whereas if we're looking at a pure substance, element's going to be on the periodic table. Compound is going to be a formula of some kind. And I'll give you the formula. So it won't be like, I don't know, should this be a formula I know? All right. So let's do this one then. Okay. So here's what I want you to do in this one. In the first column, I want you to classify these 8 examples as a pure substance or a mixture. Okay, so you can just put PS or M. That's just down that first column. The second column, if it's a pure substance, I want you to tell me, is it an element or a compound? If it is a mixture, tell me, is it homogeneous or heterogeneous? So everybody got that? Okay. So first go down through the first column. Is it a pure substance or a mixture? Go down the second column and identify pure substances as elements or compounds. Identify mixtures as homogeneous or heterogeneous. We've got 4 minutes. All right, so some of these ones were pretty straightforward. Some of them you're probably going to need a little more information. Maybe you knew this, maybe you didn't. So NaCl, did everybody get pure substance? Okay, so you see the formula, pure substance. And is that an element or a compound? Compound. So because it's NaNCl, and you can see both of those on the periodic table, that makes it a compound because it's more than one element. Now, 10 karat gold. Does anybody know what the carat thing means? That's how pure it is, okay? So you can have 10 karat, you can have 14 karat, and you can have 18 karat gold. 18 karat gold is actually like the highest gold content. If you had pure gold, it would bend. You would never be able to make jewelry out of it. It's too soft. So what they have to do is they add zinc and other metals to it to make it harder. So 10 karat is sort of the lowest gold content all the way up to 18. So what does that tell you? It's a mixture, because it's a mixture of various metals. So it's not just gold, but it's got other metals in it to actually make it harder. So when you look at something that's 10 karat gold, can you tell where the gold is and where the other metal is? No, it's all kind of a gold color. So that makes it homogeneous. All right, salt water. Salt water is a mixture. Homogeneous or heterogeneous? Homo. If you took a cup of water, add a teaspoon of salt, stir it up, completely dissolves. You can't see the salt crystals anymore. So homogeneous. Oxygen gas, pure substance. It's a element because it's on the periodic table. Now, unstirred paint. So when you go buy paint at Lowe's, if they don't stir it, what does it look like when you open up the can? It's got like this liquid layer on top, okay? If you buy latex paint, there's water on top. If you buy oil-based paint, it's an oily layer. And what do you have to do? You have to stir it, okay? So you have to stir it to be able to make it look uniform. So if it's unstirred, it's a mixture. And what would you say? In that one, it's hetero because you're going to have that layer up on the top. Now these ones you might not have known. Ammonia. Ammonia is NH3, so what would that be? It's a pure substance, and it is a compound because nitrogen and hydrogen. So if you see two elements written together, you know that's going to be a compound. Now the air in this room is roughly 79% nitrogen, 21% oxygen. So that makes this a mixture. And is it homo or hetero? Homo. You can't see it, right? Now when there's fog, then you can actually see there's a high water vapor content and it actually collects and you can see it. But under normal conditions, the air is homogeneous. And then here's the last one. Lord, if they don't ever quit paving, 64. Okay, they have been paving 64 since April. Okay, since April. I've had a bunch of students get tickets. I will tell you when they say 55, do not go into that 55 mile an hour zone flying at 70. I have had students walk in, I got a ticket. I don't know who it was that said they never got a ticket. Do not speed in those 55 mile an hour zones because they do pick people off. Okay, but what do you know about asphalt? A mixture of what? What do you think? What's the stink that you smell when you drive by the big tar? Yeah, so there's tar. That's what like holds it all together. But then they actually, have you seen the thing looks like a dinosaur? It's the one, it's actually like eats the old asphalt, grinds it up, and they reuse it, which at least they do that. At least it doesn't end up going in a landfill. So they actually reuse the old asphalt, grumble it all up, add more tar to it. So it's got rock, sand. In fact, there is ground glass. Have you ever noticed sometimes, especially like if the sun's going down, sometimes you'll notice like there's almost like a weird sparkle or shine to asphalt, they actually add small amount of ground glass because it's a little more reflective. So it can actually help you see the road better at night because your headlights bounce off of it. So it's got all of those things. So that makes this a mixture. And then it looks, if you get up close to it, it's hetero because you can see rocks. Like if you go out in the parking lot and you look down, you can see rocks in the asphalt. So up close, you can see those layers to it. Okay, so I am going to stop there for today.